we've gone through geometry, and we know the general gist of the shape of molecules. Okay, these shapes are in direct correlation to what their polarity is, which is what we are going over today. Now, these shapes determine a lot of how these molecules interact with each other, because if I have two molecules like this, and I needed this center atom to interact with this center atom, it's going to be very difficult to get past these other atoms, right? If this was a linear molecule, it would be much easier. Okay, so the shapes affect how molecules would interact with each other, but also the polarity affects the interaction. Okay, what is polarity? Polarity, just like anything, if something is polar, it's either hot and cold, or it is the opposite of each other at the same time, right? Okay, it's either happy and sad at the same time, it's hot and cold at the same time. Okay, there's a polarity to it. In terms of molecules, in terms of chemistry, it is the molecule's charge that is polar. Okay, what are our two charges? Positive and negative. So, if a molecule is polar, that means it has a section of it that is positive and a section of it that is negative. Does that make sense? Okay. So the polarity is a molecule's charge on opposite sides of the molecule. Okay, this is key, and we'll find out why later. Okay, so on a molecule, you not only have to have opposite charges, but they have to be on opposite sides of the molecule. Okay. Questions so far? Okay. Who can remind me what electronegativity is? Raise your hand. I'm probably spelling something wrong there. Maddox.
Electronegativity is like how much a certain element or whatever needs electrons.
Right. So it is an element's want or need for electrons.
You also spelled that correctly, by the way.
Appreciate it. Okay. It is an element's or an atom's want or need for electrons. Now, as we've said before, atoms and molecules do not have personalities. Okay, they are not alive. So want and need are a very
Personification.
Yeah, they're a personification of a molecule. It means that they are more stable with electrons or without. Okay? So electronegativity is the want/need for electrons. Okay? How do molecules complete their octet? By bonds. Okay? The octet rule is met through bonding. Okay? For instance, let's look at a bond between hydrogen and chlorine. Okay, this is hydrochloric acid, stuff that's in your stomach. Okay. Hydrochloric acid is just one hydrogen and one chlorine. Now, hydrogen wants how many electrons to complete its octet? 2. It'll get that through the bond. Chlorine wants how many? 8. It needs one more, which it'll get from the bond in hydrogen. Okay? There are 2 electrons here in that bond that are being shared between the hydrogen and the chlorine, correct? What type of bond is that if they're sharing electrons?
Covalent.
Covalent. Okay, if they're sharing electrons, they are covalent. Now, just because they are sharing these electrons does not mean that they are sharing them equally. Okay? It's not like a 50-50 give and take. Not all the time. Okay? So, that determination of if they are shared equally or not depends on their electronegativities. Depends on the atom's want for electrons. Okay? There are actual numbers associated with this, and I'll get into those in a second. But as a general rule, if you have two elements bound together, oh, that looks like a smiley face. If you have two elements bound together and they are not the same element, it is most likely a polar bond. Okay? There's most likely an unequal sharing of electrons. The only exceptions to this would be if they are two of the same elements, so an A bound to an A, or if you have carbon bound to hydrogen. Okay, these are our two exceptions, making them non-polar. Otherwise, they are sharing equally. Okay. If you have two of the same elements, they have the same electronegativity. And so the electrons being shared between the two would be 50-50. Okay? If you have carbon and hydrogen, their electronegativities are so close together that it is essentially like they are sharing it equally. Okay? So, unless you have two of the same elements or a carbon and a hydrogen bound together, you're going to have unequal sharing of electrons. Does that make sense? You guys with me so far? Yeah.
Is there any others like carbon or hydrogen?
Probably, but in terms of this class, we only need to know those. Okay? Any other questions? Okay. On our hydrochloric acid here, between the two of them, well, first off, do we have two of the same elements bound together? No. It is hydrogen and chlorine, two different ones. Is it a carbon and a hydrogen? No. So that means these bonds are being shared unequally. Looking at our periodic table and on our trend of electronegativity, which one has the higher electronegativity, chlorine or hydrogen? Raise your hand. Simon.
Is it hydrogen? No, it's up one row.
Chlorine doesn't need as many as hydrogen would.
They both need the same amount, but it's chlorine because it's farther up and to the right. Not farther up, but it's farther to the right. Okay? In terms of where hydrogen's electronegativity is actually placed, it's somewhere in between boron and carbon, I believe. So it's like somewhere in between there. But all you have to know is this. Okay? So chlorine has the higher electronegativity, which means those electrons being shared in this bond here are not being shared equally, and they're spending more time with the chlorine. Okay? Now these electrons move very, 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 very fast. Okay, they're very small, they move very fast, and they don't have to go a very long distance. So, in terms of average time spent, it's almost as if the electron is spending the majority of its time with chlorine and only a little bit of time with hydrogen. Does that make sense? Okay. In chemistry, if we have an excess amount of electrons in one area, it becomes what charge? Negative. So, in this molecule, with the electrons spending the majority of their time with the chlorine, we end up getting not a full negative charge, but a partial negative charge on the chlorine end and a partial positive on the hydrogen end. Okay, that little squiggly looking D is a lowercase delta. You don't need to know that. You just need to know that it means partial. Okay, it's not a full charge. It is a partial charge. Okay, we have a partial positive on this hydrogen over here and a partial negative on this chlorine. Okay, and that is the idea or the gist of polarity. This bond right here is polar. Okay, it has opposite sides of the bond, opposite charges. Does that make sense? Okay, now as you can imagine, this affects how it interacts with other molecules. If it was to interact with another polar molecule, the negatives would go towards the positives and vice versa. Okay, so it involves or it affects how the chemistry would work on the molecules. Does that make sense? Okay, two polar things are more readily interactable than a polar thing and a nonpolar thing. Okay? Questions so far? Okay. What we just showed is a polar bond. And the only reason this is a polar molecule is because there's only one bond in the molecule. Okay? When we get into multiple bonds, we get into more sticky situations. Okay? It is harder to tell whether a molecule is polar or nonpolar. Okay? So, moving on to multi-atom molecules, I'll give you an example of carbon and hydrogen. So let's take methane, CH4. We have methane here. It's just carbon and hydrogens. If I look at those bonds, would any of them be polar? No. Why?
Because hydrogen and carbon are non-polar, they should say.
Right. It is a carbon-hydrogen bond, and so their electronegativities are so close, they're essentially sharing those electrons 50-50. So, we do not have any polar bonds here, which means there's no set of partial charges. Would that make the molecule, the entirety of it, polar or nonpolar?
Non-polar?
Nonpolar.
Non-polar bond?
Yeah. They're all nonpolar bonds. So there's no way for this molecule to get charges on either side of it. Okay? All the electrons are being shared equally. And so, this is an example of a nonpolar bond giving a nonpolar molecule. Does that make sense? Questions on that one? Okay. Now let's say, instead of all carbon and hydrogens, I now have one of those hydrogens replaced by a fluorine. Okay, this fluorine is now bound to a carbon. What can we say about the fluorine-carbon bond? Haley, what do you think? Think it would be polar or nonpolar? Carbon and fluorine. Yeah, it would be polar. It is not a carbon-hydrogen bond. and it's not two carbons and not two fluorines. So it would be a polar bond between carbon and fluorine. Which one, the fluorine or the carbon, is more electronegative? Maddox?
Fluorine.
Fluorine is more electronegative than the carbon. Okay, so Grace, where would the partial negative charge be? On the fluorine. Okay, we would end up getting a partial negative charge on the fluorine side of the bond, and then the partial positive would be on the carbon side of the bond. So right now we're still just looking at bonds, and we're not looking at the molecule as a whole. We're just looking at the bonds inside the molecule. Okay? These carbon-hydrogen bonds are still what? Nonpolar. Okay, it's carbon and hydrogen. So it's a nonpolar bond. Yeah?
Can you explain again why carbon has the positive one and fluorine?
Yes. So fluorine, when compared to carbon, has the higher electronegativity. It has the higher want for electrons. So the electrons in the bond are going to spend the majority of their time around the fluorine and then some of the time around the carbon. So the majority of time that the electrons are over on the fluorine, it gives a partial negative charge. And then when they're on the carbon's fine. But when they're over on the fluorine has almost a full set of, or it's almost an ion at that point, right? It has all of the electrons it would need. So it's almost a negative charge. And then when the electrons are over there, this carbon has a lack of electrons, which would make it positive.
But I thought for the hydrogen fluorine one, the fluorine has the positive.
Did I draw that?
Okay. I got that.
Okay. Does that make sense though?
Yeah.
Okay. EJ, you have two fluorines, they're going to share equally, right? So it would be a nonpolar bond. Okay.
Wouldn't it be a polar molecule? Because it's like polar in it?
We'll get to it. Okay. So right now, we've just determined whether or not the bonds are polar. Okay. Now, to determine if the entire molecule is polar or not, we have to look at where the charges are at on the entire molecule. Okay. Which is where our geometries come into play. Okay. The way it's written right now, it doesn't really look like one side of the molecule is positive and one side is negative, right? Just has to do with this little area right here. Okay, but if you look at it in 3D, in the tetrahedral form, like this, okay, you can see that one side of this molecule would end up being negative, and the other side, right here, would be where the positives would be, right? And so, since there is one side negative, one side positive, that makes this entire molecule polar. Okay? This side of the molecule is negative, this side is positive, and so we have a polar molecule. Does that make sense?
Okay, wait.
Mm-hmm.
So, because the fluorine is like partially negative or whatever,
Mm-hmm.
but the hydrogen is not, that's why it's a polar atom because they're on opposite sides.
Yeah.
Okay.
Okay. Do you have a question, Emma?
What if it's not on top?
We'll get to that in just a second. That's our next example. Okay. Any other questions? I encourage them. Keep them flowing. Yeah.
Why is carbon and hydrogen not polar?
Because the electronegativity of hydrogen and carbon are so close together that their difference is essentially zero. Okay. Yeah.
Do you have a Band-Aid?
I do not. If you'd like to go to the nurse to grab one, you can. Yeah.
What if you have like a whole other like thing going on and like sharing a bottle of fluorine together?
Like over on this side?
Yeah.
Well, it won't happen with fluorine, but we'll get to an example where that might be a problem. Haley?
So, since carbon and hydrogen are so close,
Mhm.
when you have carbon with another one, would you give it the same electronegativity as hydrogen?
I'm sorry, say that again.
So, like if I had my periodic table,
Mhm.
let's say it was like carbon and fluorine or something,
Mhm.
you'd still get like hydrogen's electronegativity.
Carbon and who?
Hydrogen, do they have the same for
No, so essentially, if you're doing the trend on the periodic table, hydrogen is essentially right here between carbon and boron in terms of what its number per electron is. And so it's much closer to the carbon than it is to boron. So when those two are found together, it's non-polar. But when the hydrogen is found with something like oxygen, it is.
Okay.
Does that make sense? Okay. Any other questions? Annie, you had one.
How do you know if the one side is positive?
That this side is positive? Because since the carbon is positive, or partially positive, it's going to draw the electrons towards it, which makes this end positive. Does that make sense? Okay. Question? Here's just a thumbs up. Okay. Yeah.
And so, if the carbon was partially negative, then would that make the hydrogen on the opposite, like that side, would that make that side negative because the middle one is negative?
Not necessarily.
Okay.
I don't know if I quite understand the question,
Okay.
but
Well,
let me
because
get to the next
Okay.
example and it might answer it.
Okay.
Okay. All right. So we've labeled this one as a polar bond, which leads to a polar molecule. Okay. This last example for today is going to be carbon dioxide. Okay, and this is where the shape really comes into play. Okay. Now, Cohen, if we're looking at the carbon-oxygen bond, just the bond itself, not this molecule, would it be a polar or a non-polar bond? Polar, because it's not between two of the same elements or between carbon and hydrogen. Okay? Yeah. So oxygen is more electronegative than carbon, and so the oxygen is going to hold more of the electrons than the carbon will. Okay, the oxygens want the electrons more, and so those electrons that are being shared would be shared unequally towards the oxygen side.
Oh, so they both have the same amount, one just has the strongest.
Yeah, yeah. It's essentially like if I was, let's say, this end was the carbon, and that end near my desk is the oxygen, and I'm an electron, okay? Electrons move very fast, and so I said this was carbon, right? And that was oxygen.
No, I believe that.
Don't mess me up, Maddox.
I'm sorry, I'm talking to myself.
Okay, so if I'm the electron and I'm running, it's like there's something sticky on the ground over here, so it sort of slows me down. And then I get across the sticky part, and I get over to here, and it's not sticky, so I can turn around, and then it gets sticky again. So I'm spending more time with the oxygen, and then it doesn't get sticky, it's fast, and it gets sticky again. Okay, does that make sense?
It makes so much more sense for me. I
So this from turtle or Usain Bolt?
Well, then go back to before I did that.
Okay.
Yeah.
Is it fair to assume
Makes
that
so
the
much
ones
more
with the
sense to me.
circles are probably going to be the negative ones?
You mean the one with the dots?
Yes.
So.
In general, sometimes, yes.
Why is one oxygen, one
No, they aren't. I'm only looking at, like, I'm ignoring, if I'm only looking at the bond, I'm only looking at this carbon and this oxygen. And then I'm looking at this carbon and this oxygen. Okay. No, so I'm the electrons in the bond between one carbon and one oxygen. Okay. Fast.
Same way on the other side?
I understand.
And then it would be the same on the other side.
Okay, that makes a lot more sense.
Okay?
Yeah.
Does that help?
Yes.
Okay, now. What's up?
I have a better.
We'll get to it later. Okay? Now, we now know that the carbon-oxygen bond is polar. Okay? And it lends itself to the negatives, come on, being on the oxygen sides, right? That looks like an 8. It's not supposed to be an 8. Which means the carbon would be the slightly positive, right? You with me so far? Okay. This is where the shape comes into play because carbon dioxide is what shape? Linear. Okay? It's straight across like this. Okay? So these two green ones are my oxygens, and that's where the negative charges are. And then right dead set in the center is where the positive is. Even though these are polar bonds, the shape does not lend itself to a polar molecule because if I approach it from opposite sides, I have a negative over here and a negative over here. That's not two different charges, it's the same charge. Okay? If I approach it from this side, I get an amalgamation of positive and negative, a mixture of positive and negative. I just like the word amalgamation.
That's pretty cool.
Okay? So if I approach it from this side, it's going to be a mixture of positive and negative. It's not going to be one or the other, right? DNA?
Yes.
Okay. So that makes this molecule non-polar. Okay? It has polar bonds, but it makes the molecule in its entirety non-polar.
Is it balanced out?
Essentially. You can think of it as they're pulling in opposite directions, and so they kind of cancel each other out.
Oh.
Okay?
To be polar, it has to be like a magnet.
Yeah, it has to be like a magnet where one side is positive and one side is negative. Okay? That's what polarity is. So this is an example of a polar bond, but a non-polar molecule. Questions? Yes.
Okay, so back to the question that I had earlier
Sure.
with the second example.
Okay.
So you said that because the central
Guys, stop talking.
because the central one is like partially positive,
Mhm.
that it technically makes like the hydrogen on the other side also positive.
Yeah, because
Would
it's
it
like
be the
the
same thing if like the middle one was negative? Would it also make the hydrogen technically negative too?
yeah, because it's like if this is positive, it's going to start drawing electrons towards it,
Okay.
which makes then these hydrogens positive
Okay.
because they have a lag. But if this is excess, it's going to push the electrons away
Okay.
essentially, and the other side. would be
Okay.
in excess.
I just figured out how to word it, so
Okay, cool.
it made sense. So you could answer.
There you go. What's your example?
Okay, so I made a batch of cookies, and I'm sharing them with Madison. But she just has the worst cookies because they're smaller. But I get the bigger, stronger cookies. But we both have the same amount of cookies.
Sure, if that makes sense, go for it.
No. No.
Jenna,
Why does the hydrogen
these charges are only based off of this bond.
Oh.
Okay, and then the result of that would make these somewhat positive. Does that make sense?
No. When I first see the polar, I think it's like, oh, the water one. What's that word again?
When something's like.
Oh, water vapors. Yes.
I mean, yeah, that's part of it.
Hydrophobic, yeah, that's what I know it is.
All right, so We are going to end up or wait, no, I already have it written down. Okay, we're going to work on polarity again tomorrow. This will be, simple ones, will be on the quiz. Okay? Quiz is still on Monday.
This is honestly an issue. This is actually the hardest part.
What?